Do I still have more time or? Oh, thank you.
Thank you very much, Kim. I think it's about the time we start the meeting officially, Barbara.
Oh, thank you. Happy Valentine's, everyone.
Sorry. I am here. Um, not quite sure where the camera is. Hello, everybody. It is 7:30. Time for the meeting to start. If people want to come and take their seats in the auditorium, those of you out in Zoom land are welcome to sit or stand as you please. Sorry, we're getting arranged. And thank you, Kim, again. That was
Thank you so
a
much.
delightful concert. We really appreciated it.
Happy
And
Valentine's.
happy Valentine's Day.
And
We
happy
actually can
Friday
hear
the
it in
13th.
well, Friday the 13th is a lucky day for us.
Right. Glad to be with you guys. Thanks.
Yeah. Anyway, welcome. As Kim commented, this is Friday the 13th, which is, we like to think, an auspicious day for a meeting. And so far, things have been going reasonably well. So that's a good thing too. Um, in case you have no idea who I am I'm Barbara Toy. I'm the current president. It's a pleasure to see everybody here in the auditorium, and I wish I could see people out in Zoom land as well, but unfortunately I'm not able to. Before we get started with the club announcements, we have a library giveaway, which Doug and Greg are going to handle. So hold on just a minute. Let me give the microphone to Doug.
Thanks, Barb. Well, every month we're going to have a giveaway of books because we have a surplus of books. Thanks to Jake and Karen, who is in the library. Tonight we have one book. Normally we'd have several piles of books, and I'll tell you how I'm going to do it. Instead of just guessing numbers, I'm going to have numbers be in a series. You know, like the specific gravity of chromium, Avogadro's number, the first two numbers of all the NGC numbers in Delphinus. There aren't any. So if you hear the first numbers being bid, you may get an idea what the sequence is. But I'm Scottish. I may be related to Turning. I don't know. So there may be some little tweaks to the numbers. So the number thing is between 0 and 100, but not 0 and not 100, and not more than the designated number. And if you get it, you get the books, either a bag of books or in this case, one book. And Greg knows the number. Do you know the number? Don't tell us. Don't tell us. You know the number, yes? Okay. So this is the photographic lunar atlas, the entire atlas in a somewhat dilapidated cover, but the pictures are wonderful. This is Apollo program vintage stuff. Maybe it's pretty old, but it's everything on the moon and wherever it is. No date. So you don't get a date with this. 1960? Wow. Okay. So you got your number? Your intuition is probably better than you're trying to think of a series. Got your number? We're going to go around and see who wants, if you want to have the books, raise your hand and tell me a number. Raising your hand and tell me a number? Yeah? 33. Away in the back? 13. Okay. What? 92. John? What? 63. I can't hear you. 87. Wait, Greg. Okay. 47. 42. 73. Is that it? What's the number, Greg?
31.
She was too high. That's too high. What's the number underneath that? 27? Who had 27? You get the book, get the books. Got to come down and get them. Well, that makes it more interesting. I won't use that series of numbers again. Do you know what it was? Pi. 31 is 3.1. Oh, I may use it again. No, I won't use it again. So every month we're going to have an auction of books. And Jake, will we have a telescope in the very soon? Jake, will we have a telescope auction very soon? No, not for a while. So you need to stay tuned to the Serious Astronomer and various announcements to find out when we're going to have a telescope available. And but in the meantime, we'll have plenty of books. Okay, Barb? Thank you, Greg.
And congratulations. Raisa, do we have Kyle on? Or should I do the announcements?
No, we do not have Kyle.
Okay, then you all are stuck with me doing the announcements. When we get the PowerPoint to start up again. Different PowerPoint. Okay. Okay. So you all know that you are here for the meeting. This is the roster of those who actually were elected in the recent trustee election. This is the 2026 board. We're very happy to be welcoming Greg Shedcheck, who you saw up here with the moon book, and let me see, Liam Kennedy was joined us in around September. Anyway, we're looking forward to having a good year, and if anybody is interested in seeing what the board actually does, the board meetings are open to the membership. Just let Alan know that you are interested in attending, and send him an email. He'll be happy to send you a link so that you can attend. Welcome new members. The current batch, we're very happy to have you. It's Jeff Gate, Alric Jason, Vanilla Krishman, Juan Leal, Ethica Gutierrez. I have no idea. I probably really messed that first name up. I'm sorry. Mark Morin, Peter Powell, and Gabriel Santander. Are any of you here tonight in the auditorium? Welcome. We're really glad to have you. And welcome to all the rest of you who maybe, I hope some of you at least are on Zoom. For those who have not yet received your badge or picked them up, they're over here on, yours should be, or maybe down here on the whiteboard. If it's not there this meeting, it should be there by next meeting. And if you aren't picking it up at the meeting, ultimately it will be mailed to you. This, of course, is the badge that identifies you as somebody who can participate in club events. And some of us manage to mislay them almost immediately, but we still go to club events. Okay, the Cosmic Corner Cafe is, or the Cosmic Cafe Coffee Corner is upstairs. It's kind of in a corner, I guess. It's more on a passageway. For those of you who are at the meeting, you can enjoy wonderful coffee and donuts and water and company and all the great things. If you are on Zoom, you're just going to have to provide that for yourself. But you know, you can come to a meeting in person and maybe enjoy them as well. We have upcoming star parties. Upcoming star parties at ANZA on February 14th, which just happens to be tomorrow night, and maybe will be clear. We don't know. There is a storm coming in, but we're hoping it'll be postponed long enough that we can actually get a decent star party this week. We have the Orange County star parties actually coming up, and the latest word from the county is we may actually be able to have the one that we are hoping to have in March. So stay tuned. We'll keep updates coming on the website. It's been a long time coming. If any of you are interested in helping out with these star parties, we're hoping to get sort of a group of people who can be coordinators or assist with a different star party so all the burden doesn't fall on one person. Please contact Alan. That's Alan at ocastronomers.org. And you know, it's the plan here is not for it to be a burden to anybody. We would like to have a team so that that the responsibility can be spread out and everybody can have fun. Anyway, we have special interest groups coming up as well. The Astrophysics SIG is meeting on February 20th. The beginners class, the next beginners class will be March 6th. And the Astroimaging SIG is going to be going to more online discussion groups or an online discussion group format. And you've got the website or the link there to get to it. Yeah, the link should be on the website as well. Then the next board meeting is March 22nd. So as I said, if you're interested in finding out what we do, email Alan and you can attend and find out. The Messier Marathon. We always do this every year. Right now, it's formally starting on March 21st, but actually anytime around that period is good if March 21st doesn't work for you. That happens to be one of the 2 star parties for ANZA that we have in March. Anyway, that's the night where you can hopefully see all of the Messier objects in one night. And we've actually had members that are able to do that. For me, I would say if I claimed to be doing it, it was probably hallucinating, at least on the early and the late ones. Yes, sir. Congratulations. Great. Yeah. Our outreach coordinator was advising us that he actually was able, with a bit of expenditure of energy and time, to do the Messier Marathon photographically, which is another level of challenge. However you want to do it, it is it is a fun activity, and we recommend it. There should be Messier Marathon forms available on the website to assist with that. The Adopt-A-Scope program is still alive and well and thriving. Please get hold of Jake if you have questions about it. There is a list of there's information and a list of available telescopes, I believe, on the website. Is that right, Jake? Yeah. Okay. So we do have a lot of great options, and I hope people will take advantage of that. Yes. As it happens, we now have an announcement about our illustrious outreach program, which is coordinated now by Martin Christensen, who did the the photographic Messier Marathon. Anyway, if you are interested in doing outreach events, please contact Martin. These are a lot of fun. I Yeah, as Martin was just saying, most of the events are at the schools. You get to see a lot of kids. You get to introduce a lot of interest, a lot of people to the wonders of the night sky, and it's something that they will remember for a long time. And it's a lot of fun for the people that are volunteering their telescopes. Next two events are February 26th and 27th. Martin, people can't hear you over the phone. So, but you have that information on the website, correct? Yes, and we have these are some of the upcoming ones that are currently scheduled. Martin keeps the website updated as he gets new events scheduled. So, please do go for it. I think you'll really enjoy it. And we still have the Serious Astronomer. You aren't getting it in the mail now. You're getting it electronically. But the content is still as great as it ever was. And actually, well, in some ways, who knows? Maybe some of it's even better. One of the nice things is when it's electronic, we can have color pictures without having outrageous printing costs. So that's a real advantage. If you have any articles or anything you would like to submit for consideration for inclusion in the Serious Astronomer, please contact Dave Fisher. And the ANSA site is the club's dark site, as most of you know. It is maintained entirely by volunteers, which means club members. So please, if you are out there using it, if you see something that needs being done, if you can take care of a problem, take care of it. If you are not able to, please advise the board of what may need to be done, or contact the people that are out there and that are regulars who may be able to deal with it. And if you are last on the site, please be sure that ANSA House is locked up and that the gate is latched on your way out. And please, if you've used the observatory restroom, make sure that's locked up as well. Weed clearance. We did a great job last year. We like to keep the site with its improved fire safety, in its improved fire safety configuration. With the rains, we're expecting that we will start getting a bumper load of weeds before too long. So if you're out there and can do some weed clearance, please do. And those are people that excuse me, people that have pads and observatories, please keep the areas around your area clear of weeds. And anything you can do to help keep the general use areas around ANSA House, the football field, and the club observatory clear, that would be very much appreciated. Okay, the next meeting also will be a 13th of the month, March 13th, and we hope that all of you will be here. And without more ado, we have Dr. Stephen Kane will be giving the main talk. But before that, we have our good friend, John Garrett, from the Temecula Valley Astronomers, who will be doing the What's Up presentation. John?
Thank you. And thank you, everyone, inviting me out here. It's very nice. I think you picked a night where I was particularly interested in your main speaker's topic. So I feel like, oh, okay. I just feel like you decided what would get me out here. And so you scheduled me to do this before a topic I'm very interested in. So I'm really looking forward to that. I like to do a lot of pictures, both through my telescope and with my wide field camera. I don't think any of it's that publishable publishable, but thanks to you, I have someone to share it with. So probably the biggest highlight in March coming up is we have a lunar eclipse coming. So remember to set your alarm on Monday night to see the eclipse the following morning. And if I had my way in determining all of our standards of measure, I would begin the day at daylight, so you never get this confusion about the 3rd, whether it's the following night or the morning of the 3rd. So just remember, it's the morning of the 3rd. And this particular picture I took several years ago, it captures as close to the next coming lunar eclipse as I have in my files. And so what I'm showing here is a partial eclipse being interrupted by morning. And so that's going to be similar to what we might see with this next one. We'll probably see the penumbral phase still happening, which isn't very distinct when the sunlight comes up. But you should be able to get the full eclipse, full appreciation of it between the hour or in the hour of 3 o'clock to 4 a.m. So that's when it's going to be total. And if you want to see the moon, the shadow, Earth's shadow, take a bite out of the moon, just get up before then, or don't go to bed, whichever is preferable. Anyway, so make sure that date I wrote there, January 21st, is not the date. It's that date I have at the top, morning of March 3rd. Anyway, I like to add some fresh photos to any of these What's Up. And last weekend looked like a very good weekend for me to get out and do some astronomy for sharing here. And so here I am walking out of Red Rock Canyon in Nevada. And it's a very beautiful weekend. Whenever you see that little band of shadow, that's the Earth's shadow rising right after sunset. And I usually use that as an indicator that it's a perfect night for stargazing, because you see that on really clear nights. And then about 4 or 5 minutes later, you can see that shadow rises. And so there's about 10 minutes right after sunset and right before sunrise, where we're looking down the edge of the shadow and we see it distinctly, and then we rotate deeper into the shadow, and then that effect is lost. And so here it is about to lose that effect. So it looked like a really good night for observing, but I was outside of Las Vegas, and here's what the sky of near Las Vegas is like. And the only reason you can see any stars other than the star Sirius, which is the heart of the dog constellation, is because I've enhanced the contrast to try to bring it out. But anyway, so there's a Canis Major, and the bright star Sirius is visible. And here's my portrayal of Las Vegas, and all of that light you see is from Las Vegas. However, I did point the camera up a little higher and got a picture of Jupiter. Jupiter is high in the sky in the evening, so it's a very good time to observe Jupiter. And here it is shown among the bright stars, Castor and Pollux, in the Gemini Twins constellation. And that's Jupiter right there. And one more picture from my great location in outside Las Vegas. These are the mountains being lit up by light pollution from the city. And so, I mean, it really is, if you're walking in Red Rocks, you don't need a flashlight at night, except I think I found a spot where you actually can get a really dark sky within just a few miles of Las Vegas. And this is a hypothesis. I haven't quite tested it completely. But here's an area that my son and I went climbing at. And so those mountains are about 3,000 feet above the floor of the valley. And my son and I, we climbed up to the top of that red band, and then we walked around and went the long descent, which took us down into this valley right behind that mountain. And by the time we got there, it was pitch black, and you could actually see stars so well. And my only regret is that I didn't bring a camera. And of course, we're really packing light for these kinds of adventures. And it was like, a 14-hour adventure from car to return back to car. But it was just amazing what it was like. And so I thought about that old myth about if you're in a well, you can see stars, which is not true. I put an X over it to make sure it's not true. Some of you might be wondering why I didn't give those guys a ladder, but don't worry about that. But anyway, this is a myth, but I was thinking that perhaps it's not too unrealistic that if you have a high enough mountain next to a low enough valley, and even though you've got light pollution, maybe that works a bit like that well effect. But anyway, so I don't, I have to get back there with the camera. I don't know if I'll ever get back there again. But here's a view from up there, from on top of the Red Rock, where and you know, those rocks I was talking about. Anyway, so here's a little map, a simplified map of the sky about this time of year. And the ecliptic crosses high overhead. So for the same reason that we have the ecliptic is low in summer, the ecliptic is very high in winter. Same thing with the sun and the height of the sun being very high in summer, ecliptic low in winter, sun is low, ecliptic is high. And that puts Jupiter very high over us in the early evening. And the planet Uranus is also well situated for viewing this time of year too. And another part that you might not notice because of all the light pollution that we're usually exposed to, but the winter Milky Way, this time of year, in the early evening, we are looking out away from the center of the galaxy through the thinner part of the Milky Way, and the Milky Way passes directly overhead. If you're at a really dark location, you may actually be able to see a little bit of that. And I'm going to show you a few photos that I took about a year earlier of this area first. And so what I had done is about a year ago, I went out to Anza Borrego and I was going to set up a telescope and all that. And when it got dark, I realized, oh, this is going to be no good for astronomy because there was a thin layer of cirrus clouds everywhere. And so I thought, well, I won't bother with the telescope, but I'll just set up my camera. And it turns out that a thin layer of cirrus clouds makes a perfect fog filter that will then accentuate the differences in color and brightness of the stars. And so those are some of my favorite pictures that I ever got of these objects. And so here's the constellation Orion, and here's often how it's drawn. And one of the things that fascinates me most about Orion is that those stars that make up the shield of Orion are all named Pi. Easy way to take care of things. Anyway, so other famous objects in Orion, I'm not going to show actual pictures of all of them, but the nebula that represents the sword area of Orion, if you haven't seen that yet this year, definitely do. You can see it in binoculars, and it's easy to find in a telescope. And it really is one of those objects that makes you feel good about any telescope that you might have. So definitely look at those objects. And then there's some darker objects such as Bernard's loops and IC 2118 that show up in photographs. And here's a view of one of my favorites. The whole genre of object called planetary nebulas I'm just fascinated by because they just turn out these, even when they look up like these little green dots, but they're essentially dying stars. And so there's one up there by the head of Orion, and there's a little blow up of it shown on my 8-inch telescope. And then the same telescope, no, actually that one's my smaller telescope, the planetary nebula J900. That one just shows up just like a little dot of green. I don't know if you can see it. I can't even see it from where I'm standing, but I could see it when I was looking at it at home. Then I flipped Orion this way just so I can get a little more space to show a constellation just below Orion, Lepus, the hare. And one of my favorite stars is right there, R. Leporis, and it's a carbon star, and it's a beautiful, beautiful red color. And what I did in this picture is I took this picture with my 3-inch telescope, and it doesn't look very impressive, but I deliberately misadjusted the focus in this picture to bring, just like that fog filter of my cirrus clouds brought out the color of it. So now you can probably get an appreciation for the beautiful red color. So I recommend seeing that before it gets too low in the sky this time of year. Yes. Okay. Okay, but I'm told that I don't have to look at the screen, but it's going to take some retraining here live to get used to that. Okay, next is Taurus the bull. Also photographed that night where I had some really nice clouds to make it the stars show up very well. And so here's the common portrayal of Taurus, probably going back thousands of years. And here's a few star names, and the face of Taurus is the Hyades star cluster, and the Pleiades, beautiful star cluster that's on the back of Taurus, and a few other objects that a few other objects. It's a hard habit to break. But anyway, a few star clusters in there between the horns, and then M1, the Crab Nebula. That's one of those objects that I keep saying to myself, oh, I need to get a picture of that, and I never do. And all of a sudden the winter passes, and next thing you know, it's too low. And then the California Nebula, named after our state. And in that area, there's also some of my favorites, planetary nebula again. So they're going to look a bit like little green dots. Here's a IC 2003. And then a fainter one, though bigger, is a NGC 1514. And these two are to scale. So they're taken with the same equipment. So you can get appreciation for the difference in size of them. Anyway, so Taurus, one of his horns shares a star with the constellation Auriga, the charioteer. So now we're going to go that way. And again, those cirrus clouds were just wonderful because they hardly show up in the photograph, but they did the number on the stars, which I really like. And so here's the constellation Auriga and the constellation Perseus and some objects in Auriga. Probably the first objects I ever got into looking at with my telescope was these M36, 37, and 38 in Auriga. And I'll show you the planetary nebula that's in Auriga right there. Like, yep, just love these objects. And then in Perseus, there's just so much stuff to cover. So one of the things I want to impress upon you is that we are this time of year looking through, though a thin area of the Milky Way, but through the band of the Milky Way. So we're just bound to see a lot of stuff in the sky. And going a little further, or farther up, this is back to Gemini, where I started out earlier. And here's the stars and some other objects all around Gemini. So Gemini is very high. While you're looking at Jupiter, try some of these other objects. And one more area I'm going to go into is right down here. I figure since we live so far south in the United States, it really is worthwhile to see what shows up even farther south if we can look. So I'm just kind of fascinated with trying to get as far south of a view as I can. And so here's a picture I took of Canis Major. And there's the star Sirius from Joshua Tree, the city. And here's the constellation traced out. And that star right there, just peeking up above the mountains, is the second brightest star in the night sky, Canopus. We rarely get to see that. But this time of year, once you wait for Sirius to get about as high as it's going to be, you may be able to see a little dot on the horizon, and the southern horizon, and that would be the star Canopus. And here's a group, same thing, same area. And so this is sort of my project area, an area that I hope to capture more objects with. And so here's a few constellations in that area. And then the others, the Puppis and Pyxis. And Sirius, one thing I want to point out about it is it's a good test of your optics if you can split Sirius. That is, you can see the main star and then see its faint companion. And that faint companion historically has done a lot to really revolutionize our scientific understanding of what's possible with matter. And so it's a very worthwhile thing to try to capture. And this orbit is sort of tilted, so we don't actually see it edge on. We see it kind of tilted toward us, but its companion star is right there, is about right there. And so it's actually going to be getting closer and closer to Sirius the more you delay trying to split those. So you might as well start now. You've got a couple years, but don't wait 10 years to try to split Sirius and to see its main star and its very faint companion. And it is a challenge. I've seen it, but I haven't photographed it myself. And so going on a little farther, just a few other objects. These are a bunch of Messier objects in this area around Sirius. And here is one of them, M41 in my small scope. And here is M79 in my 8-inch scope, a globular cluster. And here's M50 in the small scope, M93 in the small scope. These are beautiful clusters in a slightly larger telescope through an eyepiece. And then here's the two clusters, M46 and M47. And you might see in one of them a fuzzy green object that I'll blow up there. And that's a planetary nebula, a beautiful little composition to have that and a cluster. And so from there, another favorite star, a visual double star called 145 Canis Majoris. It is like the equivalent of Albireo, but for the winter sky. And so Albireo is well known as a contrasting pair of stars, a beautiful blue and a gold one. This is very similar to that. So definitely have a look at that. And then my favorite planetary nebula, and just a few more objects that you might see. Some of these lesser known NGC objects. and a few more NGC objects. And I think that's about it. Oh yeah, by the way, a few other NGCs. One of them, Thor's helmet, is right up there. So that's the one that looks a nebula that looks a bit like the helmet of Thor, mythologically speaking. And let's see what I got here. Oh yeah, there's a few pictures of those all taken with my little 3-inch scope. And then this is sort of my new area that I hope to scout out. So there's a lot of star clusters, even a globular cluster down low that I hope to photograph in this area, but it's all new territory to me. And I read not long ago about that one star. That's one of those objects that you can talk about, but you can't see. That is a suspected planetary collision. 2 planets hit, they think. And the basis for that is there's 2 observing programs, the WISE looking in the infrared and the All Sky Automated Survey. They published their data in which they found they're staring at the star, and then suddenly there's a big increase in the infrared. And then about 2.5 years later, both are significantly reduced. And so the hypothesis is that what they're looking at is something like this, where you have a planetary, here's our Earth, Mars, and Jupiter, but maybe 2 Neptune-sized planets about here that quite possibly collided. And by the time 2 years later, that is now the debris field is within our field of view. That is our line of sight, and that's why it might have dipped. It's one of those things that's going to be hard to say, well, if we could just see it happen again, would it do the same thing? We don't know but if it does happen again, well, that would be interesting too, because it would probably suspect that there's maybe some other explanation. But I find that just, it's one of those things that you can point to and say that might be going on, but you really can't see it unless you have quite the, not with amateur equipment. Anyway, thank you.
Thank you very much, John. A joy to be informed and entertained by your presentations. Tonight's speaker is a distinguished astrophysicist and professor at the University of California, Riverside, widely recognized for his contributions to the field of planetary science and for his engaging, accessible approach to sharing complex ideas with both scientific and public audiences. He has played a significant role in major space research initiatives and is a frequent speaker and author known for bringing clarity and perspective to our understanding of the universe. Please join me in welcoming Dr. Stephen Kane. Stephen.
Okay, how are we looking? All right.
Good.
Looks good. Okay.
There's one minor thing. We see the Zoom controls on top. Maybe if you can stop share and reshare again.
Oh, that's probably because I had...
Still there.
Floating. All right. I think this is it. How is that better?
Yes, right now. All good. Thank you very much.
All right. Thank you. Thank you, Reza, for that very kind introduction. And thank you all for coming along this evening on Friday the 13th. Happy Friday the 13th. So what I'm going to be telling you about today is the main focus of my research, which is planetary habitability. This is an extremely vast topic, and I'll just be talking through a few examples of how we consider this. But just to give you a bit of background, as you might be able to tell from my accent, I'm not originally from the United States. I'm actually from outback Australia. And I grew up there, but I've lived in the United States now longer than I've lived in Australia at this point. So when I was growing up in outback Australia, I became very interested in planetary science. Some of the events that impacted me very much were the explorations of Voyager 2. When I was a kid in outback Australia, glued to the TV in 1986, watching the images from the flyby of Uranus, and in 1989 of Neptune. And so I became fascinated with planetary science, and that is what I wanted to study. But when I was starting grad school in the mid-90s, it was very fortuitous because at that time, we were discovering planets outside of our solar system at the level where it became possible to pursue a graduate degree in this relatively new field called exoplanets. And so that was the direction that I went. And in the end, I ended up coming back to planetary science. I'll explain why in a moment. But the whole field of exoplanets has been very productive, as I'm sure that you know. This is actually a press release from a few years back when we crossed the 5,000 threshold, but now we've crossed the 6,000 threshold. And what's interesting about exoplanets is what exoplanets really brings to the table is vast numbers that enables us to use statistics. And so we can start to understand what is the frequency of different kinds of planets. So when we look at something like this, you can see that we've got about 30% of the inventory is gas giants, and then we've got super Earths and Neptune-like planets. We've only got 4% terrestrial, which makes it seem like they're rare, but that couldn't be further from the truth, because the only reason that they're a relatively small amount of the known exoplanets is because they're the hardest to find. The gas giants are relatively easy to find, and so we find those first. And so we have to understand the biases going into the way in which we discover these planets, which is one of the big challenges behind it. But what we really wanted to do was to expand our understanding of how common small planets might really be. And so we designed a mission called the Kepler mission. And the Kepler mission was launched in 2009, and it was the very first NASA mission that was designed exclusively towards the topic of discovering planets around other stars, specifically planets that might be at size of the Earth and hopefully maybe even be able to have life like the Earth is able to host life. Now, when we launched the Kepler telescope, we didn't launch it into a low Earth orbit like the Hubble. We deployed it far from Earth so that it could stare at about 170,000 stars for a period of about 4.5 years in order to look for these signatures of these relatively small planets. And it was very, very successful. It did very well, and it found thousands of planets that comprise a large part of the known inventory of more than 6,000 planets. So when we look at what we found, we see a lot of stuff like this. This is a picture which is showing some of the planet discoveries that were made. Now, of course, you all know that these aren't actual pictures of the planets. These are pictures that were created by very, very talented artists at NASA who use information provided to them to create these images of what we think that they might look like. I sometimes joke that we use genuine, made-up pictures of these planets, but the really interesting thing here is that you can see over on the right, we've got Earth by comparison. Now, Earth is the largest terrestrial body within our solar system. The smallest gas giant is, of course, Neptune. And within our solar system, we have this size gap between Earth and Neptune, which, as many of you know, that has been part of the challenge of planetary science for many, many decades of trying to understand, is that real? Meaning that, is that representative of the way in which planetary systems formed, and therefore what we expect to find elsewhere? Because I'll tell you that many of the original searches for planets around other stars did not work very well because they assumed that every system probably has a giant planet like Jupiter at about 5 AU from its star. And so that's what they were looking for. But it turns out that other planetary systems are extremely diverse and can differ substantially from our own solar system, to the point that our system is actually kind of unusual. And one of the ways in which our system is unusual is that you can see that even though Earth is the largest terrestrial body in our system, if we go over to the left, we can see that that gap isn't very representative, because there are many terrestrial planets that are larger than Earth. In this case, going all the way from Kepler 186f, which is about 10% larger than Earth, all the way to Kepler 22b, which is about twice the size of the Earth. And so it makes those kinds of planets very, very difficult to understand, because we have no local analog of what we now call something like a super Earth might actually be like. But one of the interesting things about this is that we do have all of these terrestrial planets available to us, and we're hopefully looking for signs of life. And after all, we have an Earth-sized planet, and it has life on it. And so this is part of the challenge that we're going forward in this search for life, in looking for these planets. And because the good news is that, as you can see down the bottom, it says the occurrence rate of planets increases to smaller sizes, just meaning that smaller planets are much more common than giant planets. But as I said, they're harder to find. However, this fixation with Earth-sized planets is something which bothered me very early on in the Kepler mission, because all of the press releases, and no doubt you've seen many of these press releases yourself, Earth-sized planet found, Earth-sized planet. You might have even heard the phrase Earth-like planet. And that, of course, evokes images of beautiful landscapes and continents and oceans and life and all sorts of things that go with it. This keeps me up at night, and I realized this very early on in the Kepler mission. Why? Well, I'm going to explain what the problem is with something that I call the parable of the two villages. I want you to imagine that you live in a beautiful village. This is Riverside, by the way. No, it's not. You live in a beautiful village where everybody is able to live quite nicely, comfortably, get on with their day-to-day lives. However, you can see from your village that there are the remains of another village. And as far as you can tell, that village was the same size as your village, but now it's burnt to the ground. Nothing could possibly live there. It's completely uninhabitable. Now, you find this very disconcerting, of course, and so you ask your fellow villagers, when did that happen? And nobody really knows the answer. And then you ask your fellow villagers again, how did that happen? And nobody really knows. And then you ask what is potentially the most important question, which is, could that happen to us? And once again, nobody has any idea. I'm sure some of you have figured out what I'm talking about. I am drawing an analogy to the fact that we have a twin planet, and it is the same size as Earth. And it is an extraordinary fortune that the universe has given us, actually, to give us a twin planet and to show us that there is an alternative evolutionary pathway that differs dramatically from what has happened to Earth. And so when we look at the differences between Venus and Earth, those differences are profound, because for those of you who are not familiar with the conditions on the surface of Venus, it has a surface temperature of about 850 degrees Fahrenheit, which is about the maximum temperature of my barbecue's temperature dial that I use during the summer. And it has an atmospheric surface pressure of about 90-ish bars, more than 90 bars, which is about equivalent to a kilometer depth in the ocean, way below the safe scuba diving depth. And there's also sulfuric acid in the atmosphere. And so if you were to go to Venus, then you could be melted, crushed, and dissolved all at once. It's about as hostile as you can possibly imagine. So these two twin planets, which are the same age, they formed together, probably have the same material, had very similar starting conditions. How did they turn out differently? Well, conventional wisdom was it's quite simple. Venus is 30% closer to the sun, which means it receives about twice the amount of flux, and that's it. Job done. Venus has received too much energy from the sun. But that particular mystery has been reopened, particularly over the last decade or so, and that is because there's been a lot more knowledge that's been brought to bear on this, in particular things like modern climate models, which show that there are scenarios in which you can have habitable conditions on something like Venus. And when we look at Venus and Earth, it's not just the proximity to the sun that differs. Just about everything else other than the size is different. For example, Venus rotates extremely slowly, and it takes about 225 days to orbit the sun, but 243 days to rotate, which means it's rotating backwards. And it also has an almost vertical rotational axis, which is, of course, very different from Earth, which is about 23.5 degrees, which is the main reason that the Earth experiences seasonal changes. And there are numerous other differences, such as little to no surface subduction, meaning very little in the way of plate tectonics that we observe, which is so important for Earth, for things like the carbon cycle, in recycling the carbon from Earth's atmosphere and allowing us to remain temperate. Also, very little magnetic field, no substantial moon, the list goes on. This is just a subset. So the challenge is looking at all of these many, many differences between Venus and Earth, and not just saying, oh, Venus is closer to the sun, and that's it. You have to look at each and every single one of these differences and try and calculate how much they are contributing to planetary evolution, and where are the major effects and the minor effects. And this is the challenge of planetary habitability. Now, I keep talking about planetary habitability. What does that actually mean? Well, there are numerous ways in which you can define this, and this is one of these topics where if you talk to about 10 different astronomers, you'll get 13 different answers for sure. And it can be a very controversial topic as well, particularly when some folks are very cavalier about using it. And this is where astronomers get into trouble all the time if they start, for example, talking about Earth-like planets as though they have any idea about whether these planets have habitable conditions, much less whether they have life on them. So where do we even start? And that is a big part of the question. As much as we try to not be too anthropic about this whole topic, there is one place where we can reasonably start, at least to have a conversation, and that is it all going okay? Oh, it did? Okay, we're good. We can reasonably start with talking about surface liquid water. And so, as we know, Earth is 70% covered by oceans. And water has certainly played an important role in the evolutionary history of life on Earth. in that that's where life, of course, started. And there's a lot of reasons to like water. Now, one of the things that I've heard some of my colleagues say is that, well, wherever you find water, you find life. That you need to be careful with the logic when you say something like that, because Earth has been, and I hope you don't mind me putting it this way, has been contaminated by life for about 4 billion years. And so that means at this point in the history of our planet, life has burrowed deep into the Earth's crust. And so you could say, wherever you find anything on Earth, you find life, not just water. Life is everywhere. That's why we have to work so hard to decontaminate anything that we want to send, say, for example, to Mars to search for life there. Otherwise, you'll take hitchhikers and the spacecraft will end up detecting itself. And many of you know that that was part of the controversy with the original Viking landers and so on. And so this is part of the challenge. But like I said, there are some very good reasons to like water. And some of those reasons are that, for example, that water is extremely common. So that's great. The hydrogen and oxygen are independently common. Water is very, very common, as we know, especially in the outer part of our solar system. There's water everywhere, and there's tons of water under the ice of the Galilean moons, for example, way more than there is present on Earth. So there's a lot of water. Also, water is a neutral solvent in which biochemical reactions can take place. Now, there's alternatives to that. You can use ethane, for example, which Titan has a lot of that. But the third one is really the ace up water's sleeve, if you like, which is that water is in a liquid state at a reasonably high temperature, unlike many of the other alternatives, which means that biochemical reactions can take place relatively fast. And so for these reasons, it seems that having surface liquid water is a reasonable place to start that would optimize possible biological pathways. And so one of the ways in which we sometimes define planetary habitability is just simply as the ability of a planet to retain surface liquid water. And the surface liquid water is an important piece of this because in order to have surface liquid water, it means you need to have an atmosphere. And so that's why when somebody comes to you and says, oh, wait a minute, like the moon is in the habitable zone, so why isn't it? Well, because it doesn't have an atmosphere. So it can't have surface liquid water. And also the main reason that we want surface liquid water and we want an atmosphere is so that we could have remote detection. Because I have many conversations with my colleagues about, say, for example, the possibility of life under the ice of Europa, which is an amazing conversation to have. But if Europa were orbiting a giant planet around another star, we would never, ever know that it had a subsurface ocean, much less whether it had any life. So that's a very, very useful conversation to have about our solar system. But as soon as you leave our solar system, you must have a measurable. And the measurable is the atmosphere. The atmosphere is, I sometimes describe it as, it's like the campfire around which we can all gather and tell our stories, because that's where we get our information from, the planetary atmosphere. That is why it's useful to define planetary habitability this way. That so far sounds very simplistic, but if you look into the details of this, it starts to get complicated rapidly. Because if your requirement is, you know what, I just want surface liquid water, which is nice in a way, because now you're just saying, I want the temperature of the planet to be maintained between 0 and 100 degrees Celsius. Well, there's many, many, many things that can influence that. And this is a diagram which we call planets are hard. That's the colloquial name of it. It's basically a diagram that we sometimes use to scare the hell out of undergraduates. But it's showing you, once you start looking into this and listing out all of the different factors that will influence the evolution of a terrestrial planet, and in particular, the possible presence of surface liquid water, it becomes complicated very, very fast. So what you can see in this diagram, for example, you've got liquid water at the center, and then you can see you've got 3 different categories. And in the top left, you've got the effects of the star. Because for most planets, the vast majority of the energy received at the surface will be from the star within the system. But there are many, many different kinds of stars, and they have all these different properties of their own that we need to consider. Then you can see, of course, we've got the planetary properties, the properties of the planet itself. How big is it? What kind of atmosphere does it have? Does it have a magnetic field? Is it able to hold a moon? You know, all of these different kinds of factors, there are hundreds of them, and this is only showing a subset, and many of these are dependent on others. And then the third category, the planetary system. It's very rare that planets are on their own. There's usually other planets there, and they influence each other. They influence each other's orbits. They scatter material, resulting in impacts. And so we need to take that into account also. So all this to say is that there's a lot that we can think about, even with the relatively simple premise of, I just want surface liquid water. And having a surface liquid water, meaning a temperature range of 0 and 100 degrees, though, allows you to quantify what it is that you're looking for. Because what I do a lot in my work is I calculate energy budgets of atmospheres, and specifically energy budgets that would enable surface temperatures and pressures that would allow for the presence of surface liquid water. So what I'm going to do for the rest of this presentation is I'm just going to show you one example from each of these 3 categories to give you maybe a few ideas to think about, and I'm sure we'll have an interesting discussion at the end of it. So I'm going to start with the top left, stellar effects. And for stellar effects, I assume that many of you have heard of the Hertzsprung-Russell diagram. Has anyone not heard of the Hertzsprung-Russell diagram? Some of you have not heard of the Hertzsprung-Russell diagram. Well, I'm going to hopefully blow your mind, because I think the Hertzsprung-Russell diagram is one of the most amazing discoveries our civilization has ever made. Let me tell you what I mean. So when we look at a cluster of stars, for example, this is a cluster of stars that was imaged with the Hubble Space Telescope. And you can see that there are many different brightnesses, many different colors. And the colors are roughly representative of temperature. That's like a way to think about it. And so the redder stars are the cooler stars, the bluer stars are the hotter stars. And all these stars have different effects on planetary habitability. And as I mentioned before, stars are usually the primary contributor to a planetary climate. If you're wondering why I say usually, it's allowing for things like tidal effects like we see on Io. There are some pretty exotic planetary systems where you can get a lot of energy pumped into the planet through other effects. But it's usually the star. Now, here's what we're going to do. We're going to zoom in on this image. Now, like I said, all of these stars are at roughly the same distance, and this allows us to do a pretty interesting experiment. So first of all, we're just going to sort these stars based on color. And that means we're going to move the blue stars over to the left, and we're going to move the red stars over to the right. Then we're going to sort them by brightness. The brighter stars will be at the top, and the fainter stars will be at the bottom. When you sort just on those 2 simple axes, something amazing emerges, a pattern, which is the life cycle of stars. And this is what we call the Hertzsprung-Russell diagram. And it's an incredible thing to be able to have this snapshot of these objects, because one of the things I always tell my students about when I'm trying to get across to them how amazing stars are, and I tell them stars are naturally occurring nuclear reactors, which is incredible, and we're able to see their life cycle. Now, we have the cooler stars down at the bottom right. We've got the hotter stars in the top left. And then we've got the main sequence being the line where stars spend most of their lives, and that means they're burning hydrogen in their cores. And our sun falls right about in the middle here. Now, our sun is great for us. We are here having this conversation, so clearly it's possible to have habitable planets around stars like our sun. But what about these other ones? Well, if we consider the blue massive stars, for example, blue massive stars provide huge amounts of energy. So that's great. And you can say, well, wouldn't that be bad? Well, it's okay. You just have your planet further away from the star. But the real problem is they don't live very long. They're bigger, but they burn their fuel at a massively increased rate. And when they're done with that, something spectacular often happens. And they end their lives in one of the most energetic events that we see within the natural universe, which is, of course, a supernova explosion. And suffice it to say, that is lethal for habitability. So these stars, when I say they don't live very long, I mean to the tune of about 10 million years. And given that we're here about 4.5 billion years later, this is not great. Well, fine. Let's go to the other end. To the other end, where the red dwarf stars live. Now, red dwarf stars are very, very interesting because you often hear people referring to our sun as being like an average star. What people really mean when they say that is it kind of falls in the middle of the Hertzsprung-Russell diagram. It doesn't mean it's the most common. The most common type of stars are these ones in the bottom right, the red dwarf stars. And so there's tons of them out there, and that's great. The other thing that's really good about them is that they live a very long time, whereas the blue stars are furiously burning their hydrogen. The red dwarf stars just take their time, you know. They're one of these like people who seem to spend all the way up till lunchtime eating their breakfast. You know what I mean? So like they're just gradually burning their fuel. In fact, they spend so long on the main sequence, we've never actually seen what happens to one of them when they run out of hydrogen, because their lifetime on the main sequence is longer than the current age of the universe. So that sounds great, but the bad side of them is that they tend to be very, very active. And that means a lot of flares, a lot of events, which can also be lethal. And that's usually because they have very complicated magnetic fields. But this results in these flare events, which, as I'll show you in a moment, can be bad for planets. And so we've got these different kinds of stars with different kinds of energies. How can we consider that when we're looking for planets that might be suitable in the search for habitability and perhaps even life? And this is where this concept of the habitable zone comes in. You may have heard of it before in the context of the kind of press releases that I was talking about. When somebody says, oh, Earth-like, then that usually means that they've discovered a planet which falls within the habitable zone of its star. So what is the habitable zone? Habitable zone is the region around the star within which a planet could have liquid water on its surface, given a dense enough atmosphere. Once again, requiring an atmosphere. Doesn't mean that the planet has life. No, not necessarily. May not even have liquid water because it may not have had water delivered to it in the same way that Earth received its water. So there's a lot of caveats to this, but it is a place to start. Now, what this diagram is showing is that the extent of the habitable zone, which is shown in green, depends on the kind of star. So hotter stars, the habitable zone will be a bit further out. Cooler stars will be a bit closer in. And you can see that for the cooler stars, then that might exacerbate the problem I just told you about, because if cool stars are blowing flares off into space and you're forcing those planets to be hugged up against it, that can be a nasty combination. But this is where we're going to start. Now, there are numerous examples of this, and one of the best known examples, probably, some of you may have heard of this system, it's called TRAPPIST-1. And the TRAPPIST-1 system was discovered more than 10 years ago now. And it's a fascinating system for a number of reasons, but one of the main reasons is that it has 7 planets that we know of. It could have more, But from those 7 planets, at least 3, maybe 4, depending on how you count them, fall within the habitable zone, this green region around the star. Now, another fascinating thing about this system is that if you look closely, you can see the solar system is shown by comparison. But look closely, you'll see that it says enlarged 25 times. And actually, if you put that entire TRAPPIST-1 system inside of our system, you can see that it'll just, this is it right here. It's adorable. It's this tiny little miniature thing. And it falls well within the orbit of Mercury. So it's tiny, tiny. And so how is that possible? Well, because the star here, the host star, is about as small as a star can be and still burn hydrogen. If it was any less massive, it would not be able to burn hydrogen. It would be a brown dwarf instead. And so it's right at that limit. And that means that the habitable zone is right up against it. And so these are the kinds of planets that have been really the focus of a lot of activity. Because if M dwarfs are so common, and they have these crazy nice systems where they've got lots of planets which are all around about the size of Earth, then that might mean that these kinds of systems are the best possibilities to study the evolution of planetary habitability. Well, this brings us to the second topic, planetary properties. Planetary properties. So there's a lot of different things that you can study about planets. And of course, one of the reasons that we've been so excited about the TRAPPIST-1 system is because now we have a new toy, which is the James Webb Space Telescope, which was successfully launched Christmas morning of 2021. I believe it was something like 4:30 a.m. local time. And as was said before, about like when it's that early in the morning, rather than get up, you can just stay up. And that's exactly what I did. I stayed up all night playing video games, waiting for Santa. And I knew it'd be easier to do that than to try and get up at 4:30 to watch the launch. And it was very successful. Now, I'm sure there are many of you who have a background in engineering, and there are hundreds of different mechanisms that had to take place throughout this deployment. And if you're engineer minded, what that translates to is hundreds of possible points of failure. Yeah. Yeah, exactly. And especially this part right here, where it's deploying the solar shield. Without that, because that was just held under tension. And so when that was deployed, is just let go the tension, and hopefully it deploys successfully. Without that, it wouldn't have the protection from the sun, and the telescope would have been largely useless. Now, fortunately, everything went amazingly well, not just with the transformation of this compact object into this glorious telescope, but the deployment to the Lagrange point on the opposite side of the Earth from the sun, where it was able to do its observations. And because of that, it saved a lot of fuel. And so the deployment of JWST was very exciting. So how does that help us? How does that help us with something like TRAPPIST? Well, what we can do with some of these planets is that we can use an amazing geometry that the universe gives us with cases like this. And that is, when the planet passes between us and the star, then it sets up an incredible opportunity to conduct an optical experiment. So when the planet passes between us and the star, that means the light from the star passes through the atmosphere of the planet on its way to us. And in the process of doing that, some of the light is absorbed by the atmosphere. And what exactly is absorbed and how much depends on what the atmosphere is made of. So, for example, if there's oxygen or carbon dioxide or sulfur dioxide, all these various things. And so it produces a very specific fingerprint, which we refer to as a spectrum. So whenever we are using the James Webb Space Telescope to look at the atmospheres of a planet orbiting another star, which frankly is a very, very incredible sentence to be able to say out loud that we're doing that, well, that's what's happening. That's what's happening. We're looking at the absorption features from the atmosphere. So what do we expect to see? Well, We can use the example of Earth. So Earth, what would we see if we were aliens and we were looking at our planet as it crossed in front of the sun and the atmosphere was absorbing some of that light? Well, we would see all kinds of interesting things. We would see, for example, evidence that there's presence of land plants. We would see evidence of volcanic activity through the production of carbon dioxide and sulfur dioxide. We'd see evidence of massive amounts of cows farting, you know, things like that. And also, we would see water vapor, because water vapor absorbs very, very well, and could be evidence that there is surface liquid water and that water vapor has evaporated into the atmosphere to produce that effect. So these are the sorts of things that we're looking for. Right, so now that we know what we're looking for, and we've pointed JWST at the TRAPPIST planets, what did we see? Let's take a look. Well, this isn't very good news. So one of the possibilities that had been considered very much was we knew that M stars, like these cooler stars, were going to be a problem because of what I said earlier, because of their giant flares. And we knew that if you put a planet in the presence of these constant high energy flares, then what that will essentially do is it will blow the atmosphere off the planet, and very, very efficiently. And so if we have these planets orbiting this TRAPPIST-1 star, which, by the way, is about 7.5 billion years old, so it's quite a bit older than our sun. So these planets have been suffering under these conditions for quite some time. So what did we see? Well, what this is showing is what we expect to see if it had an atmosphere, which you can see here, compared to what you would see if there was no atmosphere. In other words, no evidence that was any kind of medium that was redistributing the energy received from TRAPPIST from the day side to the night side. And it's very, very consistent with the worst possible scenario, which is, you can see this quote right here from the abstract of the paper where this was published. The most straightforward interpretation is that there is little or no planetary atmosphere redistributing radiation from the host star, and also no detectable atmospheric absorption from carbon dioxide or other species. Our best evidence so far indicates that TRAPPIST-1b has no atmosphere. It is something that essentially looks a lot like Mercury, except larger. And so we've been doing this experiment not just for TRAPPIST-1b, but for TRAPPIST-1c, D, E. So far, all of them are consistent with not having any atmosphere. And this is, of course, a big, big problem if we want to consider these stars as beautiful places where you can have lots of habitable planets. So how do we understand this further? Well, once again, we have to return back to home and look to our nearest neighbors, because we do have a neighbor on the other side from Venus, Mars. And Mars can teach us a lot about this. Mars is about half the size of Earth at about 1/10 of the mass, has about 38% of the surface gravity, and a similar percentage of the energy that Earth receives from the sun. So Mars is an interesting experiment in looking at how atmospheric loss works. And it's something that we have observed. We know that Earth is losing its atmosphere. We also know that Venus is losing its atmosphere. We've seen it from spacecraft. But the thing about Venus and Earth is that they are both still volcanically active, and they replace what is taken away. Mars, on the other hand, hasn't had significant volcanism for a long, long time. So some of you probably know that the atmosphere of Mars is actually a pretty good vacuum. It's like 0.6% of Earth's atmospheric pressure. So it's very, very low. So how do we know that this is happening? Well, there is a spacecraft called MAVEN, a NASA spacecraft, which is PI'd by a friend of mine, Shannon Curry, over at University of Colorado in Boulder, and that's been monitoring the Martian atmosphere for the past 12 years. And this is a simulation showing the effect of the solar radiation hitting the Martian atmosphere. And you can see in this simulation, it's making a prediction about the way in which the atmosphere is blown away from the planet. Now, the data from MAVEN matches the simulation almost perfectly. When we see the simulation data come up, that is representing exactly this bow shock effect of the solar radiation. And there's a couple of reasons for that. One is that Mars does have very little magnetic field. And so when there's ionized or charged particles, it's not able to effectively deflect them, but also because it has very little surface gravity. And so it's unable to hold on to its atmosphere. And so we see this effect even for our sun at this distance that is significantly further away from the sun than the TRAPPIST-1 planets are from their star. And their star is much, much more active. So this is something that we've been able to understand the physics of. By the way, the MAVEN spacecraft, sadly, some of you may know this, passed away not so long ago. It went behind Mars and we didn't have contact with it when it came out the other side. So, but hats off to the MAVEN program, because it only had a nominal mission lifetime of 2 years, but it lasted 12. So like many of the successful NASA missions, it went way beyond its expiration date and did a fantastic job. All right, so third one, planetary systems. Now, this is something which is very, very dear to my heart, because I think a lot about our solar system architecture in the context of habitability. And one of the things I love to do for myself, but most particularly for my students, is thought experiments. And that means that take our solar system, the planetary system that we know the best of any. Now let's just make one small change to it. Let's move this planet. Let's put this over here. Let's increase the temperature of the sun. You just change one thing, and then you ask your student, what would change? If you just change that one thing, what would change? And an amazing question for our students is, if we get rid of Jupiter, if Jupiter would never formed, what would Earth look like now? And I'll tell you why that's important. As you know, our planetary system has an incredible amount of debris left over from the formation of the solar system, the asteroids. And the asteroids are spread throughout the solar system in all of these different groups, which are largely representative of the kind of material that was condensing into these asteroids at the time when the solar system was forming. And so as we move out further from the sun, you can see that, as we expect, that most of the asteroids are falling between Mars and Jupiter. And many of you will know that there's a particular reason for that. For those of you who are history buffs like myself and obsessed with things like the Titus Bode law, when that was originally formulated after the discovery of Uranus, and predicting that there should be these other planets and things like that. And when Ceres was discovered with the aid of a telescope, they called it a planet. In fact, they called everything a planet until they got to about 24 planets in the solar system, and they said, hang on a second. There's something going on here. And so they declassified many of the asteroids, which is very eerily similar to what happened not so long ago with Pluto. But we have all of these asteroids here, and the thing that's really governing a lot of this is Jupiter, because Jupiter is more massive than all of the other planets combined. And its gravitational influence throughout the solar system is profound. And it has absorbed a lot of these asteroids, and it has scattered a lot of these asteroids. And of course, many of us have seen this. So this image right here will look familiar to many of you. That is, of course, the impact of comet Shoemaker-Levy 9 on Jupiter, which I believe was 1994. Is that right? Someone will correct me if I'm wrong. 94. I was in my third year of undergrad. I had my own telescope at that point, and I had pointed to Jupiter, as did everybody. Even the relatively new Hubble Space Telescope was pointed at Jupiter, which took these pictures. And we saw in real time the effect of a comet impact on a planet like Jupiter. And we saw these series of explosions as the pieces of the comet plowed deep into the atmosphere and caused a deep explosion within the planet. And any one of those, of course, would have been an extinction level event if that had been for Earth. And that was a stark reminder that, oh, thank goodness we got Jupiter. Because, of course, that happens all the time. We just happened to see one of those. And it happened a lot more in the past. One of my colleagues likes to say that integrated over time, the biggest cause of death on Earth is impact events. And so when you go back to the deeper history of Earth, there were a lot of impacts. And of course, we see evidence of that just by looking at the moon, which is a great impact museum, as I call it. But Jupiter is very, very interesting because on the one hand, it can absorb these impacts that otherwise would have been a big, big problem for life on Earth, but it can also scatter things in our direction, because it can take material that would otherwise have remained benign in a harmless orbit around the sun and send it our direction. And so that's a big part of the role of Jupiter in scattering material. And in particular, as I mentioned earlier, there's a lot of water at the outer part of the solar system, tons of it. And some of it makes that way to the inner part of the solar system because of Jupiter. And so in this thought experiment, when I say to people, okay, let's get rid of Jupiter. You know what? To hell with that. Let's just get rid of Saturn as well. And let's try to imagine what effect that might have had on Earth and the habitability of Earth. Well, there's several possibilities. One is that Earth may have had less water delivered because there wouldn't be these giant planets to move things in from the outer part of the solar system. But this could be really, really important. And the reason is because we now know enough about other planetary systems to know that actually planets like Jupiter and Saturn are relatively rare. And when I say relatively rare, I mean at about the 10% level. Only 10% of other planetary systems have giant planets that are farther from their star where they can scatter icy material inward. And so having these giant planets may be important. And if all of these other systems don't have them, then that could be incredibly critical to the whole story as well. So I want to finish up by just going back to Venus. Because as I mentioned at the beginning, Venus, I think, has a lot to teach us, and Venus is the main part of my research. And the reason is because Venus is an incredible opportunity to take two planets side by side and play a game of spot the difference and calculate what the consequences of those differences are. And this is particularly important for Venus because it may not have always been like this. And this is true of any planet, by the way. If you think about our Earth, and if you look at a picture of our Earth, then you say, well, that's the Earth. If you were in a spaceship orbiting Earth about 2 billion years ago, then you'd look down at it and say, oh, I wonder what planet that is. You wouldn't recognize your home planet, probably. Continents would certainly be different, and a very, very, very different ecosystem. You go back 3 billion years and you probably got no chance because the atmosphere would even be a different color. And so all of these planets are changing through time, and there's very good evidence now that Venus once looked like this. It had surface liquid water oceans at some time in its past. We know that there is very strong evidence that it has lost a lot of water. We see that in things like what we call the deuterium to hydrogen ratio in its atmosphere, which is evidence of massive amounts of water loss. And so this is quite profound because it means that going back to this alien civilization looking at us scenario, if you were an alien civilization looking at our solar system 2 billion years ago, you would say, oh my God, there's 2 Earth-sized planets, both of which have surface liquid water ocean. And maybe they both have life on them as well. But things move forward and things change. And when we're looking at planets around other stars, it's important that we understand how planets transition from one state to another state. And that's why we have to go back. Now, I won't go into the history of the exploration of Venus, which is very interesting on its own, particularly the Soviet Venera program. But suffices to say that Venus has been largely ignored over last few decades. And thankfully, over the past decade or so, since myself and others have been working on this, that interest has come back because of the recognition that in order to understand planetary habitability in other systems, we have to look in our own yard. We have to look at the nearest Earth-sized planet. If we can't understand Venus, then we've got very little hope for understanding a planet that is 100 light years away, and most of the time we can't even see it. So thankfully, that message was heard by NASA. And so during the pandemic, in the middle of 2021, it was announced that there have been numerous new missions to Venus selected. And there was a competition where there was 4 missions competing against each other. One to visit Io, one to fly by the Neptune system called Trident, which would have been awesome. And there were 2 Venus ones. So I thought, we've got 50-50 chance. And actually what happened was both of the Venus missions were selected in a clear message from NASA that, yes, Venus matters. And so Da Vinci and Veritas, I'm on the science team for Da Vinci, and the Da Vinci mission is going to be a lander. It's going to drop a probe into the atmosphere in a 45-minute descent profile all the way down to the surface. Veritas will be mapping the surface at much higher resolution than ever before. And so we'll have much more detailed maps of the surface and understand the potential geological activity that's present on Venus and whether there's any ongoing surface subduction, which I mentioned earlier. All of these pieces are of the puzzle that will tell us the history of Venus and whether it could have had surface liquid water in the past. Because if we can understand that about how you get from a planet that has a surface of surface liquid water and beautiful conditions to the current hellscape that we see for our sister planet, then not only will you learn a lot about the past and future of Earth, then you will also learn about how we more effectively search for these features on planets around other stars. So I'm just going to end it, but I have a few topics here which may spark some interest. This is just like a sample of some of the kind of questions I like to ask, but there's hundreds of these kinds of questions. It's a whole lot of fun, and I look forward to hearing any of the questions that you might have. Thank you very much for listening, everyone. I appreciate it. Yeah, that is entirely true. So for those of you who may not have heard, the comment was that there's a giant spectrum of biological possibilities that is vast and goes beyond even things like using liquid water as a solvent or even that temperature range, right? Because even on Earth we see extremophiles which go outside of. Exactly. And one of the things I'm always talking to my students about is that we always have to be conscious of this tendency towards and being anthropic about this, like always looking at the Earth. Like, for example, when we look at the Earth, we say, oh, life is here. We have a weirdly large moon. So the two must be, well, maybe they are connected, maybe not. But when it comes to the evolution of life on Earth, there's a few things that we need to be very, very concerned about. One is, like you say, that the life progression on Earth is only a subset of all possible pathways, but also that we're looking at a particular history, 4.5 billion years. And as I mentioned, many of these planets that we're seeing around M-dwarfs in particular are much older than that. So even if you have much slower metabolism, then then there's other possibilities that exist. So I absolutely agree with you. In the words of Dr. Ian Malcolm, life finds a way. So I think that's a really important thing to keep in mind for sure. And by the way, one of the reasons that, you know, as I mentioned, when some of my colleagues publish a new discovery, they can make a big deal about a planet being Earth-sized, and they call it Earth-like and things like that, trying to make people excited about, oh, another Earth. And my feeling is that, well, the way in which we really should get excited is not for something which is identical to us, because we already know this works. The really exciting thing would be to find something which is completely not like Earth, and yet it has life on it. Yes. Good question. So the question was, if a planet has life, how do we detect it? And this goes back to what I mentioned before about the spectrum and using Earth as an example. Now, Earth as an example, we see combinations of things like methane and carbon dioxide, for example. Methane and carbon dioxide and oxygen and various species like that. Now, oxygen and methane in particular are very, very reactive. And so they will naturally convert into CO2 and water. And so you should remove the methane very, very quickly. And so we refer to that as being an atmosphere which is in disequilibrium. And so you could infer possibly from that that means that there is something producing the methane. But then you need to be really careful, because then the temptation will be to jump over here and say it's biological. Now, it could be biological, but methane can be outgassed from a planet. It can be outgassed. That's no problem at all. So you can get what we call abiotic production of methane. So the real big challenge is when you're looking at the spectrum of a planet, this is once again where we have to be super careful, because we're thinking as Earthlings on Earth and what works for us and what we see in Earth's atmosphere. And because sometimes you'll hear people say, we don't know what we're looking for, but we'll know it when we see it. And my response is, I'm not sure that we will. There could be things in plain view and we'll completely miss it. So this is where it comes back to that important aspect that you was talking about of mapping out all the possible chemical pathways and all the possible metabolic byproducts that will have a detectable presence in the atmosphere. So it's really challenging. It's something that myself and my colleagues are still talking about when we detect a different combination of species, how do we convince ourselves that it's life? And it's going to be hard, because there will be non-biological processes that could potentially, all you need is one person to come along and say, I know how you can do that with a volcano, right? That's all you need. And then you're done. You can't prove it's life anymore, because there's been one possibility found. So it's a tough problem. You don't see any? There's a question out the back. Thank you for that question. That is, I love that question, because there was discussion earlier during your great presentation about Sirius and about the other component to Sirius, and that is a stark reminder that the majority of stars within the galaxy exist in binaries. And when we were talking to people about it, the numbers vary. You may have heard a lot of numbers yourself. Sometimes you'll hear 50%, sometimes you'll hear up to 85%. And a big part of the reason for that is because many of the companions are very, very small, like in the case of Sirius B, which is a white dwarf. So you can barely see it. And so the point is that it's another way in which our solar system is unusual. And so we do need to think about that very carefully, because if we only thinking about a single star in the habitable zone, then we're not representing the vast majority of stars. Did you have a number for that? I'll get back to that in a moment. No, because that's a really important point. But to address your question, essentially it means that you need to take into account the energy received by that planet from both stars. But here's the rub: when you're only considering a single star, it means that everything is spherically symmetric. It's very, very, very easy. One of the things I love to talk to my students about is the Isaac Asimov story Nightfall, if any of you have read that. And one of the reasons I love talking to them about that story is because it's a very definite message from Asimov to say, don't be anthropic, because somewhere else in the universe, there's an alien civilization saying that we can't exist. But one of the interesting things about that story is that they speculate at some point, imagine a system with only a single star, and the planet orbits that star and rotates very rapidly. There's no way that planet could have life. But the interesting thing about that is that they have 6 stars in their system, and it's extremely complicated for them to calculate what's happening for them. Whereas, Galileo and Newton and Kepler, who we hold in high regard, to them, they were playing on easy mode because we only have 1 star. And so, like I said, everything's spherically symmetric. And so when you have multiple stars in your system, you have to calculate the energy received from each star. And it's very analogous to the problem that Laplace, well, Newton and many others were trying to solve, but Laplace did solve, which was the movements of the planets in the solar system by essentially adding up the gravitational perturbations from each planet at each moment and then adding that all up. That's essentially what we do when calculating the habitable zone for when there are multiple stars in the system. But the other last point I'll make about that is that means the habitable zone is always changing because the stars are always moving. And the stars, you maybe have 2 stars which are orbiting each other in the middle, kind of like a Star Wars Tatooine scenario. And it means that the energy is fluctuating up and down and up and down. And so it creates a different climate. Does that answer your question? So your question
can
about...
we get...
Sorry. Yes, what was that?
Questions from online audience?
Was there an online question?
Yeah, there are a couple. Is that a right time to ask?
Oh, let me just deal with a question that was asked before I finish this one, because your question was, if we find life, if I'm getting this right, you said, if we find life or don't find life, then so what? Is that what it was? Yes. So the question is, for those of you who are online, if we do find life elsewhere, well, I mean, they're so far away, communication is difficult, we can't get there, they can't get to us. It's the distance problem is not solved. You are correct. And in fact, when I announce the discovery of a new planet, the #1 question, often the first question that I get asked by the media, is how far away is it? And especially, that's why people get especially excited whenever we start talking about Alpha Centauri and Proxima Centauri, and because there's this perception that because they're the closest star to the sun, that we can somehow just pack our bags and go there. But of course, I remind them that as a civilization, in terms of human spaceflight, we have still not gone beyond the moon, and all stars are essentially at infinity for, for practical purposes, like you were saying. And so it's really about understanding the how frequently life occurs, and whether we are an extremely rare occurrence, or whether it's almost a banality of planet formation. Because one of the things that I've found over the years is that all stars have planets. In fact, it's very difficult to have a scenario where you form a star and not have planets, which are essentially debris forming out of the material surrounding the star. In the same way, it can be thought that life might be a natural consequence of planet formation, because once you form a planet, if it does have surface liquid water, then life finds a way. And one of the reasons that you could argue for that is because life on Earth seemed to start relatively early, like between 3.7, 3.8 billion years ago. So as soon as we came out of the Hadean, we seem to get life forming on Earth. Now, of course, that's just one data point, but that's where the other planets come in. It'll be additional data points to really put that evolution of life on Earth in context. That's the way I see it anyway. So, question online?
Yes. So you did talk about what happens when a planet gets infected by life, right? The chemistry changes, or use the contamination word, sorry. The chemistry changes, and those are detectable. So this questioner wants to know how easy is it to detect the chemistry of life, and if James Webb is going to be able to detect all those signs, including the oxygen in the exoplanet atmospheres.
Yeah, that's a good question. Now, the sensitivity of James Webb, as I mentioned earlier, the deployment of James Webb was very, very successful. And its sensitivity, meaning the precision of its measurements, has been, I would say, nominal. So the telescope at large is performing as we expect. Now, in terms of its ability to actually detect these biosignatures, it's difficult. And the reason that it's difficult is not just its sensitivity, from which we can detect things like carbon dioxide absorption, but it's mostly observing these stars at infrared wavelengths. And infrared wavelengths is, say, between 1 and 5 microns, something like that. And there's a very strong absorption feature for carbon dioxide at, say, 4.3 microns. And so there have been some planets where we've detected carbon dioxide and say, hey, wow, that's got carbon dioxide. Not so much for the terrestrial planets, but for maybe something a bit bigger, like the Kepler 22b I showed you earlier. Now, in order to break the degeneracy that you're talking about, that I was talking about, if you're wanting to find the evidence of, say, ozone in the atmosphere, which is an interesting other biosignature, then you mostly need to go much further over to ultraviolet wavelengths. And James Webb just unfortunately isn't quite equipped to observe at those much shorter wavelengths. So the answer to your question is that with James Webb, I think it's more of a proof of concept. And I don't know why I'm talking to the speaker. It's habit, but it'll at least be a pathfinder towards things which are coming next, because things are coming next. And what we're planning at the moment is the Habitable Worlds Observatory, which is designed to do exactly what it says on the tin. But this is something that is much further future, that will be looking at ultraviolet wavelengths. But with James Webb, we just mostly hope to get an inventory of the kind of species that we can absorb at those particular wavelengths.
Great, thank you. Another question. What is the lifespan of a habitable planet other than the life of its star?
I'm sorry, can you repeat the question?
What is the lifespan of a habitable planet other than the life of its star?
Oh, yes, great question. So the lifespan of a habitable planet other than the lifetime of a star. Well, we can, once again, we can conduct a thought experiment right here. Do we expect Earth to be habitable in, say, 1 billion years' time, 2 billion years, 3 billion years? And one of the ways I think about is that then you need to start going into the interior modeling of the planet, because planets cool. And when we look at Venus and Earth, they are geologically active. Mars no longer is. It's definitely related to the size of the planet. But there are quite good interior models for terrestrial planets now that can predict how long a planet can continue to volcanically outgas material into the atmosphere and sustain its atmosphere. And that's a big piece of the puzzle. Now, for Earth, one of the main reasons that Earth has continued to maintain its habitability over billion of year timescales, which is extraordinary. It's one of the things that my Earth scientist colleagues remind me. They say, you know, the amazing thing about Earth is that it's had water in more or less a liquid state on its surface for more than 4 billion years. And you first hear that and you think, oh yeah, okay, I guess that's kind of cool. But then you realize, wait a minute, that means it's maintained a surface temperature of between 0 and 100 degrees for 4 billion years. How did it do that when everything's changing? The planet is cooling off, it's been hit by things, the sun is getting increasingly bright. How does it manage to pull off this trick? And one of the main ways in which it pulls off this trick is the carbon cycle. The carbon cycle is the temperature-dependent process through which carbon dioxide is essentially removed from the atmosphere because it dissolves into the rainwater and into the oceans and ends up as carbonate rocks and is drawn into the interior of the Earth and then about 100,000 years later degassed out of volcanoes. And that's temperature dependent because the higher the temperature, the more it dissolves. And so Earth has this natural thermostat. Well, what enables that? Mostly plate tectonics. And once that geological processes start to grind down to a halt, then you start to lose your carbon cycle. Then you start to get a buildup of carbon dioxide in the atmosphere. And as you start to move in that direction, the water starts to evaporate. And water being transferred into the atmosphere is extremely bad because it is a very, very good infrared absorber. And so then the planet becomes even warmer and you get more water evaporated. And before you know it, you've got a runaway greenhouse process occurring and you end up like Venus. And so it's one of the interesting things about Venus for me about it possibly being a preview into Earth's future, maybe. So your question about what apart from the star, I would say the main thing is the ability of the planet to maintain its geological processes, which is able to regulate and sustain the habitable environment enabled by the atmosphere.
Thank you. We have more questions online, but let's take a few from in-person audience and then come back online.
What observations and measurements do we need to make to test ideas about planetary habitability? Yes. Mm. Yeah. Right. So the question is, how do we even approach this bottom question? You can see there in yellow, because essentially there are just so many possibilities, right? And so many possibilities for life, so many possibilities for the planet, and I'm not going to lie, it's extremely daunting. It's a very, very daunting challenge. And when I mentioned the planets are hard diagram, I had said that is when I show that to my undergraduate and to my graduate students and scare the living hell out of them. And then I have to tell them that, well, actually, this is an incredibly simple diagram, incredibly simple. There's actually hundreds of these parameters. Many of them are directly connected to each other, and that means if you turn one knob, then another one changes. And so it's an incredibly multi-parameter space. Now, something that I hinted at when I was talking about the differences between Venus and Earth at the beginning, in order to help with that, rather than just look at hundreds of planetary properties and stellar properties and think, oh my God, where do we even start? What I try and do is do some first order calculations to think, okay, what's probably going to be the most important? And what's going to contribute, but maybe at a much lower level. And some examples of that, I mean, an obvious example is how close is the planet to the star? How much energy is it receiving? But another one which is extremely important, what I call a first order planetary habitability effect, is the rotation rate. Because the models that myself and others have performed seem to indicate that actually one of the main reasons of the divergence of Venus and Earth is because Venus is a slow rotator and Earth is a rapid rotator. And that has a profound effect on the climate evolution. Now, the thing that's really disconcerting about that when it comes back to this yellow question is that we can't measure currently the rotation rate of an exoplanet. We can barely detect it at all. But trying to measure the rotation rate is not an achievement we've unlocked yet. And the fact that it is, as I perceive it, a first order planetary habitability effect, then that's a problem. And there's going to be a lot like that. For example, magnetic field. I mean, magnetic field for an exoplanet is extremely challenging. And so the way in which I see this last question is really trying to focus our efforts on those properties that I think will at least have the biggest first order effects and try to address those first and then gradually move down. But like I said, I'm not gonna lie, it's terrifying. Yeah, yeah, and knowing where to start, like I said, is a big challenge, and part of the problem is that even if we know where to start, doesn't mean that we can necessarily do that yet. I've often said that the discovery of planets around other stars is essentially technology catching up to ideas, because of course people have speculated about planets around other stars since antiquity, right? But it's only in recent years we've actually been able to do it. So the technology had to catch up. The same is true for many of these other things, because we can run these 3D climate models and go, aha, the topography of the planet matters. For example, if you have an equatorial continent, that can have an incredible effect on the evolution of the planet, which is something else that I think about, differences between Venus and Earth. But we can't measure topography for an exoplanet. So what do we do about that? And so it's another one of these things where we're doing our best to try and understand what the effects are. To transfer those into measurements, it's a big part of the challenge. Thank you. Oh, question right at the back, sorry. Sorry, the group of galaxies. Yeah, I get. Yeah, I get what you're saying. So for those of you online, the question was, It's one thing to consider all of the various properties of the solar system, but what about things that are on a much larger scale, like the scale of the galaxy or even larger? And there's a lot of work that's been done on that. I was talking about the habitable zone that exists within a planetary system, but there are those that have thought about a galactic habitable zone. And by galactic habitable zone, that essentially means that you're far enough away from the center of our galaxy, because there be dragons. In this case, a giant black hole. Or gamma ray emissions, all kinds of. But actually, there are, because of the nature of our galaxy and its spiral arms, you do get regions of the galaxy where you can get a high occurrence of star formation. And if you get a high occurrence of star formation, it also means you can get a high occurrence of the formation of high mass stars, which ultimately will give you a supernovae. And so people have thought about, well, how do we consider these regions where you're far enough away from supernovae, because that can certainly truncate not just the habitability of its own system, but neighboring planetary systems. And then there's issues beyond the galaxy that you're referring to, which is you can have galactic mergers. And all of these kinds of things, which are happening on much longer and much larger scales. When thinking about that, in adding to what I was just saying, is an already vast parameter space. It becomes even more daunting, and your head starts to explode. But but there are certainly much broader aspects on a galactic scale that you can think about, and this can be important because it could mean that there are parts of our galaxy that are preferentially inclined towards producing habitable planets, inhabitable environments. For example, the difference between open clusters and globular clusters, which tend to be much, much older and much more compact. But it also means that in globular clusters, you can have frequent stellar encounters, which can strip planets from those stars. And so there's all different populations of stars and groups of stars and layers within our galaxy, old populations, younger populations, that people are definitely thinking about as well. That's true. It's a good question.
Online questions?
Oh, hang on. She just has one follow-up question.
Okay.
I think what you just said is true, which is, she said, we're not necessarily focusing on certain areas of the galaxy that might be more preferable for life. The exoplanet surveys that have been conducted so far, like Kepler, they have been optimized towards the detection of planets, not necessarily the habitability of those planets. So they're trying to maximize the exoplanet yield of their mission. So that it's because a lot of thought went into that Kepler field of 170,000 stars to produce a field where there was minimal confusion from background contamination and all sorts of things like that. So yeah, the exoplanet surveys that have happened so far have been optimized just simply towards finding the different kinds of planets. Sorry, question online?
Yes. So you did talk about the different evolutionary path that Venus, for example, took. The questioner wants to know, has Venus ever been habitable in its life? And what conditions did it have before that might have been more suitable for life?
Well, that's the $1 million question. Well, actually, like $1 billion question, depending on how much the missions cost. Because that's something that I was talking about right at the end, because Venus definitely has changed through time. And the question is how and why. But the models that have been applied to Venus, and when I say models, I mean things like climate models, which we use for modeling Earth's climate. And they show that Venus could have had surface liquid water as recently as 1 billion years ago, which sounds like a long time, and it is, but it's only 25% of solar system history. And the reason that it's able to get away with that is because the modern 3D climate models, which means that they account for things like rotation and circulation and things like that going on in the atmosphere, they show that if you have a very slowly rotating planet like Venus, even though you're receiving more energy from the sun, you can produce a lot of clouds on the day side of the planet, which are effective at essentially reflecting a lot of the light and shielding the conditions on the surface. It can do that up to a point. If you keep turning the sun up, which it has done to itself, then eventually that will be overwhelmed. And so that obviously is what happened to Venus. Now, just because that model shows that that's possible a billion years ago doesn't, of course, mean that that's what happened. It may not have even been 2 billion years ago, might not have even been ever. Because there are other models which show that in an alternative to that, that you can get cloud formation on the night side of Venus, because the high solar radiation essentially removes the clouds on the day side. You form the clouds on the night side, which serve as a blanket, which makes the planet even warmer. So you get this double whammy effect, and then Venus has no chance at all, and never was able to condense the water out of its atmosphere onto the surface. So there's all of these possible pathways, and we don't know which one's right. But either way, I'm not necessarily a huge advocate for, oh yeah, Venus once had surface liquid water and it was awesome. But I think it's extremely profound question either way. Because if our twin planet never had that opportunity, then that's something really important for understanding Earth-sized planets elsewhere. But that possibility exists, and that's why we need to just have much better measurements. And as I mentioned at the end of my talk, Venus has largely been neglected for a couple of reasons, but mostly because once we went to Venus and realized that we can only get 2 hours worth of data with the technology at that time, mind you, because the electronics back then really couldn't handle the high temperatures and pressures. It's not very exciting to build a huge mission and then get 2 hours worth of data. But Mars is right there, and it may have had life, and it certainly had past liquid water, and so attention has gone back to Mars. But now we can do so much better on Venus, and it's such a lucrative target. Our data for Venus is remarkably poor. So just having a better data will help us answer the question that you asked.
Thank you. The next questioner wants to know about Area 51 in Nevada. Have you used your credentials to inquire Air Force about the supposed aliens there?
I've never tried to pull rank on anybody at Area 51.
Thank you. That was it online.
Yes. So the question was that for the planets are hard diagram, it was observed that some of the parameters, the writing was in yellow, some of it in green, some of it blue. That was essentially indicating whether we can currently measure those or how hard it would be to measure those. So essentially the ones that were in green were ones that we can currently measure for a lot of different kinds of planets. Whereas the other colors are indicating that more work needs to happen before we can actually unlock those achievements.
Thank you so much.
Welcome. Thank you.
Be able to be around for a little while. And our speaker will be able to be around for a little bit longer for those who may have some further questions they want to talk to him about. It's been a great meeting, and we look forward to seeing you next month. Have a great Valentine's Day.